Okay, let's dive straight into this explainer and uncover exactly what examiners are secretly looking for when grading those high-stakes electrical energy and power questions. I want you to imagine this for a second. The exam hall is dead silent, the clock is ticking down, and you turn the page to a massive, imposing 8-mark question on your Cambridge physics paper. It's a complex circuit scenario, and it's asking you to evaluate the cost-effectiveness of a household appliance. Right here, in this exact moment, is where dreams of an A-star are either made or completely broken. You see, I've spent an unbelievable amount of time analyzing thousands upon thousands of past papers across the Cambridge syllabus codes. Whether you're sitting the 0625, the 0651, the 0652, or even the 5054 and 9702, the pattern is identical. What I see over and over again is a tale of two very distinct types of students. Let's call them Alex and Sam. Now, Alex is our textbook regurgitator. Alex overloads the page with raw, unfiltered physics facts, literally writing out every single equation under the sun, but provides absolutely zero analysis. It's just a wall of math. Sam, on the other hand, is our speed demon. Sam rushes through the question, completely missing the specific command word requirements, just desperately trying to finish on time. They both lose massive grade-defining marks, but for entirely different reasons. Well, today we are going to fix that. We're going to take those flawed, leaky answers and transform them into top-tier, airtight responses. Think of this like being a street artist. You want to make your mark, you want to show bold strokes of creativity, but that masterpiece absolutely relies on a solid, undeniable structural framework underneath.
So, what actually separates a solid B grade from a truly elite A-star in IGCSE Physics? The crucial point to understand is that grasping the raw physics concepts is literally only half the battle. Seriously, the rest of the war is entirely about how you strategically structure your answers. An A-star isn't just about having a better photographic memory for formulas, it's about the execution. It's the strategy. When our friend Alex looks at an electrical power question, they just see a math problem to solve. But when a top-tier student looks at the exact same question, they see an opportunity to demonstrate a deeply connected conceptual understanding. The Cambridge assessment objectives are specifically designed to test your ability to apply your knowledge to completely unfamiliar, real-world contexts. If you just memorize formulas without understanding how to decode the examiner's highly specific command words, like knowing the exact difference between calculate, determine, and evaluate, you are just leaving easy marks sitting on the table. You are essentially painting without a canvas. We need to build that canvas today. So here is our agenda. First, we'll hit the core principles. Second, we'll decode the kilowatt hour. Third, the methodology sequence. And finally, examiner warnings.
Section 1. Core Principles. Let's start with the theoretical architecture.
Before you can build that masterpiece, you absolutely need to understand your tools. In Cambridge Physics, your primary tools are the fundamental assessment objectives, knowledge with understanding, handling information, and problem solving. But to consistently secure those top-tier marks, we need to apply a rock-solid structural framework to these tools. I call this the PEEL framework. P-E-E-L. That stands for point, evidence, explanation, and link. Let's take a look at the classic equations. P equals IV and E equals IVT. Power is current times voltage, energy is current times voltage times time. Sounds super simple, right? But let's look at how Alex answers a typical question using these. The exam asks to explain why a specific fuse is chosen for a 230-volt appliance drawing 10 amps. The command word here is explain. But Alex just writes P equals 230 times 10 equals 2300 watts. And they get 0 marks for the explanation part. Why? Because Alex didn't use the PEEL framework. They didn't analyze. Let's do a quick interactive challenge right now. I'm going to start a mental 30-second timer. Listen to this rewritten answer and see if you can spot the PEEL structure. Ready? The appliance draws an operating current of 10 amps. We know this because power equals current times voltage. Therefore, a 13-amp fuse must be selected because the fuse rating needs to be slightly higher than the operating current to prevent the circuit from breaking under normal use while still protecting the appliance from a dangerous power surge. Boom. Time's up. Did you catch it? The point was the 10 amps. The evidence was the P equals IV concept. The explanation was why the 13-amp fuse is slightly higher, and the link tied it directly back to the safety context of the question. That is how you decode command words. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Now, what's really fascinating is that candidates who reference cross-topic connections to these fundamental principles achieve significantly higher marks across the board. For instance, connecting electrical power to thermal physics is a massive win. If a question asks about an electric kettle boiling water, an A-star student doesn't just lazily calculate the energy using E equals IVT and move on. No way. They use the Peel framework to link that specific electrical energy to the thermal specific heat capacity equation. They actively show how the electrical energy transforms into thermal energy to raise the water's temperature. And crucially, they acknowledge real-world limitations, like the fact that not all electrical energy is actually transferred to the water. A significant amount is lost to the surrounding environment as dissipated heat. That is exactly the kind of critical, evaluative thinking that examiners are desperately hunting for with their red pens. That is how you deliver a truly perfect answer. Section 2, the kilowatt hour. Let's see how this builds into practical applications.
You must completely master the precise definition of the kilowatt hour. It is the absolute non-negotiable foundation for all appliance cost calculations you're ever going to encounter. Let's define it clearly. A kilowatt hour is the energy transferred by a 1 kilowatt device running continuously for 1 hour. Now let's bring Sam back into the picture. Sam was faced with this question. Calculate the cost of running a 2,000-watt heater for 3 hours given a rate of 15 cents per kilowatt hour. Sam, being our speed demon, rushes it. Sam grabs their calculator, takes 2,000, multiplies it by 3 to get 6,000, and then just multiplies that by 15. The examiner's red pen immediately strikes it out. 0 marks for the final answer. Why? Because Sam missed the absolutely critical foundational step of unit conversion. Sam failed to convert watts to kilowatts before doing the math. Let's do a live rewrite right now and transform those red marks into green check marks using our physics success blueprint. I'm going to give us a 60-second mental timer to fix this. Step 1. Identify the given data and convert. Power is 2,000 watts. We must divide by 1,000 to convert this. That gives us 2 kilowatts. Step 2. Time is already in hours, so 3 hours is perfect. Step 3. Energy in kilowatt hours is power in kilowatts multiplied by time in hours, so 2 times 3 equals 6 kilowatt hours. Finally, step 4, apply the cost. 6 kilowatt hours multiplied by 15 cents gives us 90 cents. Look at that transformation. That is how flawed, panicked reasoning becomes a full-mark answer when you follow a rigorous step-by-step structure instead of just frantically mashing numbers into a calculator.
Section 3, the methodology sequence. Let's unpack the exact procedural framework you need.
Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCS, to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, let's get into the interactive workshop part of this explainer. Knowing the formulas just isn't enough anymore. This standardized 5-step sequence is your absolute roadmap to logical, structured reasoning in every single exam question. Let's kick off Challenge 1, the data scan. Imagine a massive, complex data table showing the current and voltage of various household appliances over a 24-hour period. I'm putting a 60-second visual timer on the clock in our minds. If you just start looking at the raw numbers, you are already losing. Step 1 says identify key elements. You should be laser-focused on the column headers first. Are the currents listed in amps or milliamps? Because if it's milliamps, you have a conversion trap waiting for you. Are the times in minutes or hours? The core trend extraction here isn't about doing the math right away. It's entirely about identifying the units, the anomalies, and the context before you even think about touching your calculator. That's how you lock in those method marks from the very first second.
Furthermore, your problem solving should always utilize this 3-step micro-framework: deconstruct, solve, and evaluate. Let's jump into Challenge 2, find the flaw. I'm going to read a flawed sample physics paragraph. Your job is to identify the exact sentence that is bleeding marks. Listen closely. To find the energy used by the motor, I multiplied the voltage of 12V by the current of 2A. This gave me a power of 24W. I then multiplied this by the 10 minutes it was running to get an energy of 240 joules. Therefore, the motor is highly efficient. All right, did you spot the flaw? Where did the student go wrong? The fatal flaw is right there in the time conversion. The student multiplied watts by minutes. To get joules, your time absolutely must be in standard SI units, which is seconds. 10 minutes is 600 seconds, so the real calculation is 24 watts times 600 seconds, which equals 14,400 joules. The examiner commentary on this specific error is brutal. Candidates constantly lose out on final accuracy marks due to neglecting standard SI unit conversions. You have to deconstruct the units first, solve with extreme precision, and then evaluate. Ask yourself, does 240 joules really sound reasonable for an entire motor running continuously for 10 minutes? No, of course it doesn't. Okay, Challenge 3, speed writing. You have 30 seconds to write one perfect Peel paragraph. When you do this, you deconstruct the given values, you solve using your proven equations, and you evaluate your final number against the real world. That habit right there is what builds exam resilience.
Section 4. Examiner Warnings. Let's dive directly into the critical pitfalls.
The principal examiner reports are essentially the ultimate cheat code, and they practically scream the exact same top 3 mistakes at us year after year. Let's establish our final system here. Rule 1 is command word decoding, which we've covered. Rule 2 is Peel framework application. Now let's look at why students fail to apply it. Mistake number 1, extreme vagueness. Let's say you're asked to explain why transmitting electrical energy at high voltages reduces power loss in the national grid cables. If you just write, the energy goes down, the examiner is going to rip their hair out. What energy? Thermal? Kinetic? Electrical? You have to be explicitly specific. You must state that a higher voltage means a lower current for the same transmitted power, which therefore reduces the thermal energy dissipated to the surroundings due to the heating effect of the wire's resistance. Mistake number 2, format and presentation conventions. This literally means writing your final answer cleanly on the dotted line, explicitly stating your units, whether it's watts, joules, or kilowatt hours, and using standard form appropriately. If the question provides data to 2 significant figures, your final answer should generally be rounded to 2 significant figures. Mistake number 3 is failing to anchor your answer to the context. If the question is specifically about a wind turbine, please don't give a generic, rehearsed answer about fossil fuel power stations. Talk about wind speed, kinetic energy of the air, and the specific mechanics of that turbine.
So the absolutely crucial takeaway here is that no matter how flawless your mathematical calculation is, failing to link it back to the specific appliance or scenario is going to cost you those top marks, period. To actively avoid falling into the trap of generic answers, you need to implement Rule 3, the time management matrix, running right alongside your Peel framework. Here is the golden rule. You have roughly 1 minute per mark on these physics papers. If you encounter a 3-mark calculation question about the cost of running an air conditioner, you simply cannot afford to spend 5 minutes staring blankly at the wall. You use the matrix. You deconstruct the question in 30 seconds. You apply E equals IVT, you convert your units to kilowatt hours, you multiply by the monetary cost, you double-check your units, and you confidently move on. The time management matrix strictly dictates that you secure the easy method marks first by explicitly stating your fundamental formulas on the page. Let the examiner clearly see your logical step-by-step progression tied directly to the scenario they gave you. Don't make them guess what you were thinking.
You absolutely must shift away from simply listing vague, memorized facts and move toward evaluating limitations, questioning assumptions, and justifying your specific decisions with hard evidence. Listen to this direct comparison. This is the true A-star difference. A generic B-grade answer says, the appliance uses a lot of power, so it costs more money to run. It's true, but it's totally unimpressive. Now listen to an A-star, context-specific masterpiece. The 3-kilowatt electric oven draws a remarkably high current of 13A at 230 volts, therefore converting 3 kilowatt-hours of electrical energy into thermal energy every single hour. At a standard utility rate of 20 cents per kilowatt-hour, this results in a high operational cost of 60 cents per hour, making it significantly less cost-effective for prolonged use when compared to microwave alternatives, which only draw 800 watts. Do you hear the massive difference there? One is basically a guess you could make without taking physics. The other is a surgical strike using the precise, targeted terminology of the Cambridge syllabus. It evaluates, it compares, and it proves deep understanding.
As you gear up for your next physics paper, remember that structured methodology and context-specific reasoning are the true, undeniable keys to unlocking your full potential. You've seen the pitfalls that trap Alex and Sam, you've mastered the Peel framework, and you understand exactly what those examiners are furiously searching for. You have the complete answering system, command word decoding, Peel framework application, and the time management matrix. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.